Hey everyone, let's take a look at a problem now where we've got a tower, and the tower has some weight, and that weight is 280 kilonewtons. And then there's a wind blowing on it. Never happens in Wyoming, right? So there's this wind blowing against the tower, and that wind has a force of 200 kilonewtons, and it's acting at an angle of 36.9 degrees. That'll actually be above the horizontal, right? So the vector value is 200 kilonewtons at 36.9 degrees, which, as you should know, is a 3, 4, 5 triangle. And so that's going to be 160 kilonewtons in the x direction, or the horizontal direction, plus, because it's blowing up against that tower, 120 kilonewtons up, right? And so that's the net force due to this wind. Yeah, that's a pretty hefty wind, but let's go with it. Okay, and what we're interested in is the force moment. We're going to go specifically about A, but we're going to look at a couple of different things. We're going to look at the equivalent system, and then we're also going to look at where this force would have to be if it's going to be on the line AB, right? Or where would the line of action have to intersect the line AB? All right, so we'll start off with the net force. It's just the two, right? So my net force, if I just look at that, the sum of the forces, then I've got negative 280 kilonewtons in the j hat direction, plus 160 kilonewtons in the I hat, plus 120 kilonewtons in the j hat. And so that's going to leave me a net of 160 kilonewtons in the I hat, minus 160 kilonewtons in the j hat. So the net force is going to be at 45 degrees, and it's going to have 160 minus 160, right? So it's going to be down in this direction. So the net force, let me write that out with the red here, but the net force is going to be down like this at 45 degrees below the horizontal, with 160 kilonewtons here and 160 kilonewtons here. And so a net value of 160 radical 2 kilonewtons, right? And this is 45 degrees below the horizontal. Okay, now, the other thing I'm interested in is the moment. And so if I do R cross F in these two cases, right, I'm going to get, first off, I'm going around A. So I'm just going to go, the moment about A is what I'm interested in here. And that's going to be, this is 10 meters wide, so 5 meters times the weight. And that's going to try and rotate it clockwise, right? It's going to be down. It's going to be a clockwise rotation, so that's negative. So I'm just going to put, there should be an equal sign there. I'm going to put negative 5 meters times 280 kilonewtons. And that's in the k hat direction, right? The rotation is going to be in the k hat, in this case, into the board, hence the negative sign, okay? And then we've got this guy right here. And so as I look at that, the x component, so here's what I want to do. I want to break this down into its x and its y. So the x component is here, the y component is here. And so the x component is 160 kilonewtons, and the y component is 120 kilonewtons, and that's actually up. Right, so that's 120 kilonewtons up. And so the moment there is going to be 100, let's just look at the 160, right? So I'm taking the component perpendicular to this line up here. So it's 160 kilonewtons, and that's going to be times 15 meters. That's trying to rotate it around A, that's trying to rotate it in the clockwise direction. So again, minus 15 meters, and then 160 kilonewtons, okay, right? That's the clockwise rotation. And then there's the 120 here, okay? And the 120, that's lifting it up. So as far as A is concerned, that's going to try to rotate it in the counterclockwise direction. So that's going to be a positive moment. So plus, it's 2.5 meters, that decimal point's gone, 2.5 meters times 120 kilonewtons, and that's k hat. This is k hat, right? So these are all in the k hat direction. And if I sum those out, I should get, if I did my math right, and you are welcome to check me, 3,500 kilonewton meters in the k hat direction, and it's negative. So the net moment is going to be clockwise. And so my equivalent force couple system would be a force of 160.2 kilonewtons located at A, because I'm the equivalent force couple system around A, that's very specific. The equivalent force couple system around A. So 160 square root of 2 kilonewtons with a moment into the board. So, I hate trying to draw these things in 3D on a 2D board, but into the board at minus 3,500 kilonewtons K hat. So that's into the board. So kind of pretend that that's an arrow pointing into the board. So that would be the equivalent. Well, let me do it this way. It's going to rotate it clockwise. I'll get rid of the minus sign. It's rotating it clockwise into the board. So that would be the equivalent force couple system. Now the second part of this then is, hey, what distance am I going to be along this line AB if I put just the equivalent force so that I get the moment? So it's just the force, right? So my force is 160 I and a negative 160 J. And so I want to be along this line across here. Right? I want to be along the line AB, anywhere along the line extending left and right of AB. Where's that going to be? So let's think about it. The net moment has to be clockwise. So, and the moment is down and to the right. So it's not going to be over here because that would be counterclockwise. So it's got to be over here someplace. So the question is where? Where is it over here? All right, so let me kind of do a little erasing here. I want to get rid of this for a second. I know it's 160 square roots of 2, but more importantly, I know the net force. So it's going to be somewhere over here. I'm just going to put it right here. I don't know where that is yet. But the net force is going to be 160 kilonewtons to the right and 160 kilonewtons down. Now here's the cool thing here. It's along the line AB, right? And I'm looking for the moment about A. So it's the equivalent moment, right? So the 160 kilonewtons in the X direction, I don't care. I don't care because when I do the R cross F with this, I get 0 because R is coming off in this direction. Okay, I don't know what that R is. I hope you can see that red. R is coming off in this direction. R and F are parallel. This component of the F are parallel, so the cross product is 0. So all I really care about is 160 kilonewtons times this R. And it's going to be clockwise. And so basically the idea here is that this R distance, R times 160 kilonewtons, because that's the Y component of the force, has to be equal to this 3,500 kilonewtons. Right, so for 3,500 kilonewton meters. Those are going to be the same. So that distance has to give me the same moment. And I've taken the signs out. They're going to end up giving me a value that's clockwise. And so R is just equal to 3,500 kilonewton meters over 160 kilonewtons. And so you can see the kilonewtons go away, so I'm going to get a distance of meters, which is what I want. Those zeros go away, and I get 350 over 16. Right, 350 over 16 meters, right? And if I did my math correctly, that's 21 7/8 meters to the right of A. So it's actually going to be way over here, right? So this is not the correct distance. It's going to be someplace over here. And yeah, 21 7/8 meters, right? So this, I could do an equivalent force couple at A, or I could just have a single force acting on it over here at 21 7/8 meters. The same force, got to be the same force. The forces have to be equivalent, the moments have to be equivalent. So I would put that over there, 21 7/8 meters. I choose the line of AB because it's where these two structures are attached to the ground. And so where would that be along that line? All right, it's kind of a cool problem, a lot of different things going on, especially like the idea of the parallel component along AB has no moment, and the perpendicular component, because it's perpendicular, I don't need to worry about the angle because it's 90 degrees. So it's just R times that component, that force component. That really makes life kind of nice and easy. All right, so breaking it down to the components, big advantage there. All right, if you have any questions on this example, please leave them in the comments below. Thank you.